Hello, everybody. Welcome back. Today we're going to be looking at Unit 2.2, which is all about intramolecular force and potential energy. If you will remember back from Chem 1, the prefix intra means within. So within a molecule. So essentially, this unit is all about chemical bonds and the energy stored within them. So let's get started. So as I said, intramolecular means within a molecule. So we're going to be looking at bonds today. And the first term that comes up, the first vocabulary term that comes up in this unit is bond energy, which is exactly what it sounds like. It's the energy stored within a chemical bond, okay? And based on the number, that's going to give us information about how strong or weak that bond is. The higher the bond energy number, the stronger the bond must be. We're also going to talk about bond length, okay, which is essentially, the distance between these two atoms that are bonded. And we're going to see that two atoms will bond and the distance between them is determined by energy. Energy is always key, where the energy is at a minimum. And this will make more sense looking at this graph. So what we've got here, guys, let's imagine these are two hydrogen atoms, okay? And it actually is easier to read this graph. Instead of reading it from left to right, we're going to read it from right to left. So these two hydrogen atoms are going to bond. Excuse me. At this point on the far right, okay, the atoms are not bonded. Okay, they are experiencing forces of attraction. The electrons of one atom are experiencing a force of attraction towards the nucleus of the other atom. Remember, we talked about this in the last video. Electrons and the nucleus of the other atom should be attracted to one another because they're oppositely charged. In this middle area, okay, we're now bringing these atoms a little bit closer together, okay? They are still experiencing forces of attraction. And then this minimum dip here in the graph, this is where the atoms are going to bond, okay? So what's on the x-axis here is the distance between them. So this 0.74 and that little a means angstroms. It's just a unit of length. That is the ideal bond length between these two atoms. Why there? Because that's where the energy is at a minimum, okay? You'll notice that the energy is negative, and that is because when you form a bond, energy is released. That's an exothermic process. And that's the context in which we're looking at this. All right, I want you to imagine that we continued on this curve to the left. If I continued to push these two atoms even closer together, that's too close, and they're going to start to experience forces of repulsion. The nuclei are going to repel each other. The electron clouds are going to repel each other. And so on the left of the dip here, we have forces of repulsion. To the right of the dip, we have forces of attraction. At the minimum, this is where the forces of attraction and forces of repulsion are balancing each other out. Okay. So anywhere on this graph that we have, the more negative that number on the y-axis is, the more stable that bond is. If we, really went extreme and continued to push those atoms together, the energy would climb into the positive range, and that's very unstable. Something else to talk about. Let's review a little bit from Chem 1. Okay, we're talking about covalent bonds here. There are single bonds, double bonds, triple bonds. Let's just remember what that means. Okay, a single bond is one pair of shared electrons. A double bond is two pair or four total electrons. A triple bond is three pair or six total electrons being shared. And if you guys will recall, bond length and bond strength here are inverse related, okay? Single bonds are relatively long in their length, but they are the weakest in their strength. Whereas a triple bonds are relatively short in comparison, but they are the strongest. This will come into play a little bit later on. I just want to sort of put it on your radar. There is a term, bond order, which we will use later on. But sometimes chemists will say, instead of saying, oh, that's a C to C triple bond, they'll say that bond has a bond order of 3. Instead of saying a double bond, they'll say has a bond order of 2. Don't need to worry about it now. It's just something to go on your radar there. So I want you to look at this graph here, okay? It's the same graph that we were just looking at a minute ago, okay? But the blue dashed curve, okay, is for a single bond between some two atoms, X and Y. The red curve is a double bond. And I want you to notice two things. Number one, the red curve, the double bond curve, is deeper, has a deeper dip than the single bond curve. And let's think about what we just said. Double bonds are stronger than single bonds. So the formation of a double bond will release more energy than the formation of a single bond. So the dip should be deeper, deeper on the y-axis. Okay, that's the first thing to notice. The second thing, and it's real slight, but they've marked it on the x-axis so that you can see. The double bond curve, the distance between the two atoms is just so slight, ever so slightly to the left, okay? This double bond dip, the minimum, is at a shorter distance than the single bond curve. And we just talked about that. Double bonds are slightly shorter in length than single bonds. If I were to draw in, and I'll draw it in black so we can see it nice and clearly. If I were to ask you to draw in a curve for a triple bond, it would look something like this. I'll do my very best here to draw this in nicely. Okay, even deeper than the double bond, and again, just ever so slightly to the left. Shortest. Triple bond would be the shortest distance, shortest length. Okay, so sometimes you'll see AP questions with these internuclear distance graphs. So we've talked a lot about covalent, but we can also talk about ionic compounds. However, we typically don't discuss bond length when it comes to ionic compounds. What we will discuss, we're going to bring back the concept of Coulomb's law, and we're going to relate it to a term called lattice energy. So lattice energy, guys, is almost identical to the term bond energy. It's just lattice energy tends to be the term you use with ionic compounds. Just like bond energy, it's an indication of how strong a bond is. In this case, we're talking about ionic bonds. Lattice energy is going to be negative just like bond energy. Lattice energy is going to be negative when a bond is created, formed. Energy will be released. Lattice energy will be a positive endothermic value when a bond is broken, okay? It always requires energy to break a bond, and energy will always be released when a bond is formed, okay? That doesn't matter if we're talking bond energy or lattice energy, it doesn't matter. So there's an equation for lattice energy, which I'm hoping looks a little bit familiar to you. Okay, so E is the lattice energy. K is just a constant. You don't need to worry about it. We're not actually going to be doing any calculations with this. Just know that that constant is a positive number. Q1 and Q2, okay, we're talking about ionic compounds. So Q1 would be the charge of the cation. Q2 would be the charge of the anion. And R is the distance between them. Now I say this should look awfully familiar because it looks just very similar to Coulomb's law. The only difference being that this distance here is not squared like it was in Coulomb's law. And Coulomb's law didn't measure energy, it measured a force of attraction. But guys, it's essentially the same concept. Don't get hung up in the equation because you're not going to be calculating anything. We're going to be talking about things in qualitative terms. And again, if we're talking about two oppositely charged particles, a cation and an anion, this energy is going to come out to be negative. So we're, looking at, in this case, if it would be looking at the formation of this bond. Okay. But guess what? The relationships that we talked about with Coulomb's law are exactly the same. The lattice energy will be greater the more charged those particles are. Okay. And that lattice energy is going to be greater when those two charged particles are closer together. If you start moving them farther apart, that force of attraction is weaker and the lattice energy will be less. So it's all connected. So what I've got here is pairs of ionic compounds. And it says out of the following pairs, so within each question, pick the one with the greater lattice energy. So what you're going to do, what I would do when you're asked a lattice energy question is write the charges above each ion. So what are the charges within that compound? And think about that equation up there. Which compound is going to give you the more negative lattice energy? Okay, the more negative it is, let me explain, that means the stronger that ionic bond is. Okay, so when I say pick the one with the greater lattice energy, what I mean is pick the one that has the stronger connection. Okay, so pause your video, see if you can figure it out. All right, let's talk through these. So as I said, what I would do is write the charges above each ion. Oops, -1, okay. And think about plugging those charges in to that equation up there at the top. Which compound is going to give you the more negative product? 2 times -2 is -4. 1 times -1 is -1. So ladies and gentlemen, that magnesium oxide is the one with the greater lattice energy, the one with the stronger ionic bond. Now, If you were asked to explain this in terms of Coulomb's law, which on the AP exam, that is very common, you would simply say magnesium oxide contains the ions with, or you would, the term that I've seen them use a lot is the more highly charged ions. It's actually written on that slide right there. And thus, the ions within that compound will experience a stronger attraction. Okay. Again, let's do the same thing for the next one. So I'm going to write the charges above. Don't worry about that subscript. It's not going to affect anything. We're just looking at the charge of the ions here. Okay, now imagine multiplying those charges together. Which one is going to give you the more negative lattice energy? That's going to be this guy. Okay. So I know it may be a little bit confusing when I say that one is going to give you the more negative number, but then the instructions say which one has the greater lattice energy. Greater lattice energy, take that to mean the one with the stronger connection. Okay, how would you explain number 2 in terms of Coulomb's law? Exactly the same as number 1. Aluminum chloride is the compound that contains the more highly charged ions. Okay. Last one. Strontium is +2, iodine's -1. This is +1, this is -2. Okay. Problem. When I multiply these charges together, I get the same product. So they contain the same charged ions. Think Coulomb's law. What was the other factor? It had to do with distance. Okay. Now, do you know any, radii numbers of these elements? Do you know their bond lengths? No, you don't. But look at compare apples to apples, okay? Strontium and sodium. Find them on your periodic table. I realize they are not in the same family. I know that, but which one is smaller? That's going to be sodium. Okay, I'm going to underline it. Sodium is the smaller metal between those two. Find iodine and oxygen on your periodic table. Again, I realize they're not in the same family. That's okay. Which one is the smaller element? Oxygen. So what I'm trying to illustrate, the point I'm trying to get at here is the ions of sodium and oxygen are closer to each other than the ions of strontium and iodine. Okay, remember Coulomb's law, distance is the other piece. So here's my answer right here. Sodium oxide is my answer because although these two compounds contain the same charged ions, sodium oxide's ions have a shorter ionic distance between them. Thus, the force of attraction is stronger. Okay, so that's how you would explain it. So, ladies and gentlemen, that wraps up Unit 2.2. I hope you've learned a little something today, and I look forward to seeing you next time.